So in this lecture, we are discussing the proof of Picard's theorem. Picard's theorem states that if you have f of xy, which is a function of xy, and the partial derivative of this with respect to y, both of them are continuous on xy on a rectangle R, with the sides of that rectangle is parallel to x-axis, and if x0 and y0 is any interior point of R, let us draw a situation of what is given. Let us consider this is your x-axis and y-axis. It says that a sides of this rectangle is parallel to y-axis. That means the sides will be this is the rectangle you will have. This is your R. And this x0, y0 is the interior point inside this region. There exists a number h with the property that the initial value problem, that is y dash y of xy, has one and only one solution, which is y equal to y of x on this interval in this neighborhood of x0. So here is the point x0 you will have. This is x0. So this is the interval x0 minus h to x0 plus h. So in this neighborhood of this x0, y0, there is a function is passing through this point and exist in this point, which is your function y is equal to y of x. This is the point x0, y0, and this is the r dash. I will call this neighborhood is r dash. So it's this Picard's theorem gives you the existence and the uniqueness of the differential equation of the type y dash is equal to f of xy. When it has a unique solution or existence is there, if your this f of xy and the partial derivative of this function f with respect to y are continuous in the some neighborhood or some closed rectangle is there. A proof of this theorem is very lengthy, so keep yourself with me till then I can complete my proof, or which is given in your reference book. So we know that the solution of the equation 1, this is, I'll call it as equation 1, is also a continuous solution of the integral equation, which we have discussed also in the Picard's approximation theorem or Picard's approximation method. So we'll state that we know that every solution of 1 is also continuous solution of integral equation That is y of x is equal to y0 plus x0 to x f of t comma y of t dt. I will call this as equation 2, which we can achieve from the equation y dash is equal to f of xy with the condition y of x0 is equal to y0 by fundamental theorem of calculus. That is, integration and the differentiation are the reverse process. If you take the integration both sides, we will achieve this. And conversely, also if this is the solution of y of x is a solution of this one, this will give you a solution of that. So, and conversely we have the same thing. So we conclude that the equation 1 has a unique solution in the neighborhood of x0 if and only if equation 2 has a unique solution into the same interval. So we shall, or we conclude that equation 1 or 1 has a unique solution on an interval mod x minus x0 less than or equal to h if and only if equation 2 has unique solution on the same interval. So ultimately, if this equation 1, which is we have written in this form, and equation 2, if we can able to find out the solution of equation 1, it is equivalent to say that the solution of equation 2 is there. And in the previous lecture, we have talked about the Picard approximation method, which gives you the solution. It is in the sequence of, to define the sequence y0 of x is equal to y0. So we will define this sequence of yn, where y0 of x is y0, y1 of x will be y0 plus integration x0 to x f of t y0 of t dt. y2 of x will define it as y1 plus x0 to x f of t y1 of t dt. And if you go in this manner, in general yn of x can be defined as y. So here I just fix this y0. So y0 plus x0 to x f of t yn minus 1 of t dt, and so on. And we have proved, or we have discussed in the Picard's approximation theorem, this sequence of yn is the solution of equation 2. Okay, so it converges to the sequence of yn converges to a solution of equation 2. What is this yn? Is the nth partial sum of this series which we are defining, series of function. So we next observe that this yn of x is the nth partial sum of the series of function y of 0 plus summation n running from 1 to infinity yn minus yn x minus yn minus 1x. It is ultimately what is we have, it is y of 0 plus y1 of x minus y0 of x plus y2 of x minus y1 of x plus so on yn of x minus yn minus 1 of x and so on. So you can just observe that this y0 will cancel out. So ultimately the partial sum, this yn is the partial sum of this series. So if I can say this sequence is a sequence of yn, if I call it, this is equation 3, and this series I will say it is equation 4, or considering this series as equation 4. The convergence of this series 3, sequence 3, is equivalent to the convergence of this series. That means ultimately what I have to prove is this yn is converged to the solution of 2. If I want to prove that this sequence yn is convergent, it is equivalent to prove that this series is convergent, because this series having the partial sum is yn. Okay, so that we can write down. So the convergence of sequence 3 is equivalent to the convergence of series 4. So ultimately, if I want to prove that the sequence is convergent, if I can prove that the series is convergent, then we are done. So in order to complete the proof, we provide the number h, which is greater than 0, in the interval x0 minus h to x0 plus h. Then we have to prove the following statements. So in order to complete the proof, we produce a number h greater than 0 that defines this interval x0 plus h to x0 minus h to x0 plus h. And then we shall show on this interval the following statements are true. So the first statement that I have to prove is the series 4 is converged to a function y of fx. Second statement, the y of x function which is we have here is a continuous solution of 2 What is 2 is that integral equation. And the third one, we have to prove it is the only. So y of x is the only solution, continuous solution of 2. So this 3 statement I have to prove. In order to prove that this equation y dash is equal to f of xy with condition y of 0 is equal to y0 as a unique solution, existence of unique solution. That means we have to prove that this equation 4, that is the series, is converged to a function y of x. Y of x is a continuous function which is a solution of the equation 2. The equation 2 is this, which is the integral equation. And we have shown that to write down this equation or solution of this integral equation is equivalent to write down the solution of this equation. And we have defined this sequence of functions. And if this sequence of functions will be a solution of 2, that means this series is converged. If this series, and we have noted that the partial sum of this series will be yn. That you can just see why from this. So ultimately, our objective of proving this theorem is these 3 statements. The first one, that is this series is convergent. It's converged to y of x. That y of x function is continuous, and it is the only continuous function which satisfies the equation 2. Okay. So as per our hypothesis, we have assumed that f and del f by del y are continuous function on the rectangle. So let us we need to find out this h, how to produce this h. So we have assumed that f of xy and del f upon del y are continuous function on the rectangle R. But this rectangle is a closed subset, closed and bounded subset. Subset of R square. So we have learned one result into the analysis might be that if you have X is a metric space and F, which is a function from X to R, and if X is a compact metric space, then the function F is bounded. Since it is a closed and bounded subset of R square, so we know that the closed and bounded subset of R square is always compact, and any function defined on a compact metric space is always bounded. So according to this, continuous function is there here. Okay, so according to this fx and del f upon del y, both the functions are continuous on this rectangle, and this rectangle is closed and bounded. So that's why this function f and this del f upon del y, both of them are bounded functions. So R is a closed and bounded subset of R. So therefore f and del f upon del y are bounded on R. This is not, this is rectangle R, not that R, real line R. So therefore there exists m and k greater than 0 such that f(xy) is less than or equal to m. I will call this as a fifth equation or inequality, and del f upon del y will be less than or equal to k. I will call this as a sixth. This is true for every xy in R. This is rectangle R. Every time I'm writing that. Now, what we will do? Next, we have observed. Let us consider if x comma y1 and x comma y2 are distinct points in R with the same coordinate x. So this x is fixed. I'm picking distinct point into them. So by mean value theorem, what we can say? What is the mean value theorem? It says with respect to y. So let us recall what is mean value theorem, LMVT. F is continuous on closed interval AB. F is differentiable on closed interval AB. Sorry, open interval AB. Then there exists some value C in between AB such that f dash of C is equal to f of B minus f of A upon B minus A. So as per this Lagrange mean value theorem, our function f of xy is continuous with respect to y, and since it is given that del f upon del y is exist, that means it is differentiable with respect to y. So this function f is continuous over this rectangle, differentiable over in the interior of that rectangle. So this del f upon del y is, so I am talking about with respect to y. So by mean value theorem, we can say that there exists some y star which is in the interval this AB, but here this y1 in between y1 and y2. So this y star belongs to this y1 y2 such that f of B minus A, but here this is the point, that is x y1 minus f of x y2, and I am taking the mode both sides, upon y1 minus y2 is equal to, if I take the modulus also, so the mode of this one, it gives you mode of this, that is equal to mode of del upon del y f x y star. So there exists f dash of c. F dash of c means derivative of f with respect to whatever the variable. Here we are talking about the derivative of this with respect to y. So that is del f upon del by del y of f x y star, where y is any number which we have taken or fixed number we have. If I call this is the equation 7, this was the equation 6. Now using this sixth, what we can say here, therefore this is mode of x f of x minus fxy2 is less than or equal to mode of y1 minus y2 into k. This is because of 6. For any point xy we can say that, because 6 says that this function is bounded by k. So in particular this quantity is bounded by k, and this is true for any x1 y1 and x2 xy2 in R. And these both points are distinct points, and that not lies on the vertical line, because this x, we can write this distinct points distinct or not lies on the same vertical line. Now we'll choose. So ultimately we have to find out h. So we'll choose h greater than 0 such that k into h is less than 1, and define R dash, which is set of all xy such that xy belongs to R. So it is a subset of R such that mod of x minus x0 is less than or equal to h, and y minus y0 is less than or equal to mh. So this R dash is a subset of R. Let us try to draw what is this R dash is. So this is the situation. We have, this is your x-axis and y-axis, and you have such R is there. There is a point x0, y0 inside this rectangle R, and we are taking one R dash inside this rectangle R dash inside this R. So this is our rectangle R dash. And this x0, y0 is the interior point of this rectangle. So there is no point, there will be no difficulty to find out such h, which always will we have. So we can able to find out a neighborhood of this x0, y0. That is exactly the definition of interior point. So interior points definition says that if I want to say that x0 is or x is the interior point of some set A, then there exists a neighborhood SR of x, which is subset of A. So that's why such R dash we can able to find out. So that is a neighborhood of x0, y0 we are talking about here. You can see that how much metric space or topology is using to discuss the differentiability. So that is a collaboration of the two subjects we can see here. So we can say that since this x0, y0 is an interior point of R, there is no difficulty in seeing that such h exists. So now we confirm our attention into this interval x0, x minus x0 less than or equal to h. in order to prove the first statement, that is this. The series 4 is converse to the function y. So our objective or our concentration is now on the interval this x minus x0 is the equal to h. So now it is sufficient to show that the series y mod of x0 y0 plus mod of y1 of x minus y0 of x plus mod of y2 of x minus y1 of x plus so on, mod of yn of x minus yn of n minus 1 of x, to so on, converses. Why? Because we know that if the absolute conversion, that means mod of an is convergent, will imply summation of an is convergent. So if I can prove that this is absolutely convergent, this series is absolutely convergent, then it is say that the series is convergent. So in order to prove that statement 1, which is the series of that difference is convergent, it is sufficient to prove that it is absolutely convergent. So let us estimate this term. So we estimate the term yn of x minus yn minus 1. So that is our objective, is to estimate the term yn of x minus yn minus 1 of x. And it is first necessary to observe each function yn as a graph lies in the R dash and hence it is in R. So obvious that, so we can note that y of 0 of x is y0. So the point t comma y0 of t lies in R dash. And since it is in R dash, and we have seen that this function f is bounded due to the equation 5, inequality 5, we can say that this, so using 5, mod of f of t comma y of t, y0 of t is less than or equal to m, and y1 of t minus y0 will be, so what is y1 of t? According to the equation 3 we can have, that is integration y0 plus summation, integration x0 to x t y0 t. Now minus y0 is in this, so let us put the value of y1 here where we are calculating that distance. So the y1 value is y0 plus integration 0 to x0 to x f of t comma y of t dt minus y0. This y0 is there. So this will gives you equal to integration x0 to x f of t comma y of t dt. And so this will be less than or equal to m into integration x0 to x, mod of that I can write dt, but that is equal to m into mod of x minus x0. But mod of we are interested into the all the points which is in R dash, and the R dash is defined as mod of x minus x0 is less than or equal to x. That's why this will be less than or equal to m into h. So finally we can have mod of y1 of t minus y0 is less than or equal to mh, which proves the statement for y1 of t. That means our objective is to estimate this yn minus 1 0. So n equal to 1, for n equal to 1 we have proved that. Now to turn the inequality for the other terms, that is, which proves the statement for y1 of x. Now it follows in turn from the inequality that the point t y of t are in R dash. So f of t comma y1 of t is less than or equal to m, and y2 of x minus y0 will be as we have did it here, that is as per the definition of y2, y0 plus summation or integration x0 to x f of x y1 of t dt minus y0. So this will give you integration x0 to x f of x y1 of t dt, and that is less than or equal to mh. We can prove as we have did it here in the same manner. Similarly, we will have mod of y3 of x minus y0 is less than or equal to mh, and so on. We can prove for all the yn this. So now for the estimates mentioned above, that is estimation of yn of x minus yn minus 1 of x, that is our objective is to estimate. Since it is a continuous on the closed interval and it has a maximum, and y1 is a continuous, so it's defined as a constant value. We can say that since a is continuous, function on a closed interval has always a maximum, and we have y1 is a continuous, and we define a constant a by a is equal to maximum of y1 of x minus y0, and write mod of y1 of x minus y0 of x is less than or equal to a. Next, the point that is t comma y1 of t and t comma y0 of t lies in R dash. So using the equation number 8, which we have defined for mean value theorem. So that is the statement 8, we can say. This is the statement 8. So using this statement, what we can say is mode of f of t y1 of t minus f of t y0 of t is less than or equal to k times mode of y1 minus y0, and as per this we have taken this y1 minus y0 is less than or equal to a, so that is k into a, and we have mode of y2 of x minus y1 of x will be integration x0 to x. If I substitute the value of this y2 and y1, that is y2, we know that it is y0 plus summation x0 to x f of x minus x1 dx, and y1 is y0 plus summation x0 to x f of x minus y0 of x dx, and if you subtract this to y0 will get cancelled out, so we'll have this minus this, so that we can write f of t comma y of t minus f of t comma y0 of t dt, the mode of that. But this quantity, that is using this quantity, it is less than or equal to Ka, so that is I can say less than or equal to K into A x0 to x dt, but that is less than or equal to K into A into h, because mode of x minus x0 is always less than or equal to x, because this point x comma y, it is in that r dash neighborhood, so that's why we have this. So this is the things we got, that is mode of y2 minus y1 is less than or equal to k into h. Similarly, mode of t comma y2 minus f of t comma y1 is less than or equal to k into y2 minus y1 as per the statement number 8. But y2 minus y1, according to this, it is k into ah, so this will be less than or equal to k square into ah, and so mode of y3 of x minus y2 of x, we can write x0 to x, the mode of that, f of t comma y2 of t minus f of t comma y1 of t dt, mode is there. But again with the same argument we can say that this is less than or equal to k square ah into h, so that is a into kh whole square, and continuing in this manner, or by mathematical induction one can also prove that. We find that mode of y1 of x minus yn minus 1 of x is less than or equal to a into kh whole raised to n minus 1 for every n running from 1 to up to so on. So what we can have in the series of, now in the series, mode of y0 of x plus summation n running from 1 to infinity, mode of y1 of x or yn of x minus yn minus 1 of x. In this series, each term is bounded by this thing. So I can say this is less than or equal to mod of y0 plus summation n running from 1 to infinity a into kh raised to n minus 1. So this series is less than or equal to this much. But now, why this series is convergent? Because this k into h is less than 1. Due to that k into h we have taken it is less than 1. See, we have taken this k into h. We have choose your h in such a way that k into h is less than 1. This is the things we can have. So this is, I can say it is equation number 9. So due to this 9, it will guarantee that sequence, this series k into h raised to n minus 1 is convergent. So by comparison test, we can say that this series is convergent. Okay. So let us write with that things here. So inequality 9, which is k into h is less than 1, guarantee, because this is a geometric series, summation r raised to n, and in the summation r raised to n is convergent if r is less than 1, okay, or mod of r is less than 1. So in that case, this will guarantee that this series summation a into kh raised to n minus 1 is convergent. And so the series this, by comparison test, this series is also convergent. So by comparison test, the series y0 mod of y0 plus summation mod of yn of x minus yn minus 1 of x n running from 1 to infinity is convergent. So hence the series summation 1 to infinity y0 plus yn of x minus yn minus 1 of x is convergent. So this series is convergent. Let us say that this series is converged to y. Okay, so that means the series which we have defined, whose partial sum is yn. Okay, which we have defined this series whose partial sum is yn. So hence what we can say, let's say it is converged to, say it's converged to y of x. So therefore this yn of x is converged to y of x as n tends to infinity. Since the graph of this yn of x, so since the graph of each yn of x lies in r dash, it is evidence that the graph of y of x also has this property. That means each of yn of x is continuous, therefore y is also continuous. Okay, so now this will complete the proof of first statement. The first statement was we have to prove that this sequence of yn is convergent. That is our first objective, is to prove. The first objective was to prove that the series 4 is converged to the function y. Now the second statement, y is continuous on this. So that is, we'll prove the second part, that is this y is continuous. So now for the proof of 2, that is y is continuous. So the above argument shows not only that yn of x converges to y of x in the interval, but it also says that this convergence is uniform. So under the uniform convergence, the continuity is preserved. Okay, so this means that by choosing n to be sufficiently large, we can find, or we can make yn as closed as we please to y for all x in the interval. So more precisely, or I can say, if epsilon greater than 0 be given, there exists a positive integer n0 such that mod of y of x minus yn of x is less than epsilon for every x in that interval and for every n greater than or equal to n0. And this n0 is independent of x. It only depends on epsilon. And under the under the uniform convergence, the continuity is preserved, that you have studied in the result in the analysis. So this, since each yn is clearly continuous, and this uniformity of the convergence implies that the limit function y of x is also continuous. So it proves that now it is also a solution of, I have to prove now it is continuous and it is the solution of the equation 2. So now we need to prove, that y of x is actually a solution of that integral equation So that integral equation we have denoted as a 2. We must show that y of x minus y0 minus integration x0 to x f of t comma y of t dt is equal to 0. But we know that this is our objective, that yn of x we define as y0, so I can write down everything on the other side, that is yn of x minus y0 minus x0 to x f of t comma yn minus 1 of t dt equal to 0. If I call this is as equation number star, and if I call this is the equation number, this is the star and this is double star, and if I subtract these two equations from one another, so we'll have y of x minus y0 minus x0 to x. So from star and double star we have this xt comma y of t dt equal to so this quantity is equal to y of x minus yn of x plus summation x0 minus x f of t comma yn minus 1 of t minus y of t comma y of t dt. So what I did is I just subtracted these two equations. If I subtract these two equation, then that is equal to 0, and that 0 I can substitute that value here, this value. So 0 is equal to this side, and on the other side I have subtracted y minus yn. This y0 is cancelled out, and this minus this one we have here. Now if I take the determinant, modulus both sides, if I take the modulus here, that is mod of y of x minus y0 minus x0 to x f of t comma y of t dt, that is less than or equal to y of x minus yn of x plus, by triangle inequality, this is x0 to x f of t comma yn of t minus f of t comma y of t dt. This y of x lies in the r dash, and hence it is an r, and this is already tending to 0, so this will also tend to the maximum of, so this I can write down less than or equal to y of x minus yn of x plus kh into maximum of yn minus 1 of x minus y of x, because of the above inequality, that function it is bounded, f of x y is bounded function. So due to that we can have for that k and for h also. So uniform convergence of this yn is converging to y will gives you, this will tends to 0 as n tends to infinity, because this will tends to 0 and this will also tends to 0, maximum of that, due to the uniform convergence. So this is because of yn is converged to y uniformly. We will have, this is the reason to get this will tend to, since this is tending to 0, we can say that y of x is equal to y0 plus x0 to x f of t comma f of t dt. So hence this is the solution of the given equation. This will completes the proof of the second statement. Now, the proof for the last statement, that is, in order to prove that it is the unique solution, there is no other solution is there, only one solution is there. That is the last things is left. That is the third statement. In order to prove third statement, that is the uniqueness of that result. That means such y is unique. So we may assume that y bar of x is also continuous solution of 2 on the interval mod of x minus x0 less than or equal to h. What is our objective? We will show that y bar of x is same as y of x for every x in R. That is our in the interval for every x in that interval, we have to prove this both the y bar and y is same. So for the argument we given is necessary to show that the graph of y bar lies in R dash and hence in R. So for the argument we give, it is necessary to know that the graph of y bar of x lies in R dash and hence is in R. So let us suppose that this y bar leaves R dash. That means I have to prove that first that it is in the R dash. So let us suppose that y bar of x leaves R dash, means let us try to draw the graph for this. So this is your R. Inside there is a point x0, y0, and this is your R dash. Inside that is another neighborhood of this x0, y0. And we have assumed that y bar leaves this R dash. That means there is some y, there is some function which is outside this function. So this is the point which is leaving. So this is your y bar of x, which we have assumed it leaves the R dash. So that means it is outside this R dash. Our objective is to prove that this y bar stay in R dash. It will not leave the R dash. So property of the continuity. So continuity, since y bar is continuous at this point, we can say that there exists an x1 such that mod of x minus or x1 minus x less than h implies f of the y bar of x1 minus y0 equal to mh and y of x minus y0 is less than m into h if x minus x0 is less than mod of x1 minus x0. Now, y of x1, y bar of x1 minus y0 upon x1 minus x0. According to this is equal to mh upon mod of x1 minus x0. This will be greater than, due to mod of x1 minus x0 is less than h, so reciprocal will be greater than h. It is m h upon h, that is equal to m. So that means this is greater than m. So by mean value theorem, there exists x star in the interval x0 to x1 such that mod of y bar of x1 minus y0 upon x1 minus x0 is equal to y bar dash of x0 star. So this is the, by mean value theorem we can say that there exists x star which is in between this two. We can have this. But what is this y dash? Y dash, as it is satisfying the y dash is a solution of the our equation, that is y dash is equal to f of y dash is equal to f of x bar or xy. Y is equal to f of xy. Y dash is equal to f of xy, and y bar is a solution, so it will satisfy this equation. So that's why this is equal to f of x star y bar star. And according to this, the function, according to the equation 8, this function is always bounded by m, and this will say that it is bounded greater than or equal to m. So this is since the point, this x star y bar star, it is in R dash, and which is a contradiction with the fact that this is greater than, this statement is says that it is greater than m, this statement is said that it is less than m. So it will give you contradiction. Why we have taken this contradiction? Because we have assumed that this y bar is stay outside, leaves outside this R dash, so it has to be inside R dash. So this is contradiction. Shows that no point with the property of x1 can exist, so that the graph of y bar of x lies in R dash. So the graph of y bar is lies in R dash. In order to complete the proof now, we can, to show that this y bar and y, both of them are the solution. So that means we'll start with y bar of x minus y of x. Both this y bar and y satisfying the integral equation. So that's why with this y0 plus summation or integration x0 to x f of x comma y bar of t or t comma y bar of t dt minus y0 minus x0 to x f of t comma y of t dt. So this will gives you the integration x0 to x mod of, sorry, f of t comma y bar of t minus f of t comma y of t dt. Now since the graph of y bar of x and y of x both lies in R dash due to the equation 8, which tells you regarding the boundedness of this, which gives you that y bar of x minus y of x is less than or equal to k into h maximum of y bar of x minus y of x. So maximum of y bar of x minus y of x. So maximum of this, if I take maximum both sides, it will be k into h maximum of y bar of x minus y of x. So this will gives you, this will implies.
સર
Yes.
સાવંત સરનો લેક્ચર છે અત્યારે.
I have to finish this.
ઓકે સર.
So maximum of y bar of x minus y of x is equal to 0. Okay, because of this. Otherwise what will happen? This 1, otherwise we could have 1 is less than or equal to kh, and which is a contradiction with our assumption that this kh is less than 1, which is contradiction with the 9, equation number 9, which we have taken. So therefore it will follow that y bar of x is equal to y of x, since maximum is 0, and this is true for every x in the interval. And this completes the proof of Picard's theorem, which completes the proof. So this is the proof that gives you existence and the uniqueness for the differential equation y dash of x is equal to f of xy into the neighborhood of, or into this initial value y of x0 is equal to x0 if this fxy and partial derivative, both of them are continuous into some rectangle. So that's it for today. Okay, I can stop here. If you want, you can leave the meeting if you don't have any question.